Hi everyone, and welcome to today's video on conditional probability and independence. Now, sorry if you've loaded up Independence Day, wrong video. No aliens were harmed in the making of this particular video, but I got this feeling there's one somewhere about my head. Anyway, gilf. What is this video all about? Well, conditional probability. What is conditional probability? Hold on, I'm about to tell you. Conditional probability is about to be used throughout the probability sections that we're about to look at. All the videos I'm about to do, somewhere, there will be conditional probability. So this video is going to tell you what it is, what the formula is, and how to apply it to individual questions. It'll also look at independence, and again, no more Independence Day cracks. So what is conditional probability? Well, if I don't know, normally I load up the dictionary. Why? Because my mum, bless her, told me that if I didn't understand a word to look it up. So I looked up conditional probability, and it said the probability of an event A given that another event B has already taken place. Okay, thanks for that. An example would be good. Well, I've got an example. If I toss a coin, and I don't have a coin to toss, but I had a great sound effect, we will notice that coin will flip, and it will turn, it will land in my hand, and I'll go, ah, it's a head. Yeah? So having got that head, I'm now going to toss my coin again. And if I toss my coin again, do you think it's thinking to itself, which is obviously not, because you can't have a personality with a coin, but do you think it's thinking to itself, oh, I just got a head. I think I need to get a tail, because someone told me there's a 50% chance. No. There is absolutely no relationship between that second outcome and my first outcome. None whatsoever. So they're independent, and we'll come back to independence in a moment. Whereas if we look at the weather, imagine it's a really, really sunny day today. Do you think the probability that it will be nice tomorrow will have anything to do with the fact that it was a sunny day today? Well, actually, it may well do. But what about if it's a rainy day today and a rainy day tomorrow? Well, the chances are the probabilities of it being rainy tomorrow, given that it's dry today, will be different from it being rainy tomorrow, given that it was rainy today. So those are conditional probabilities. There is a condition of the second one relating to the first one. So, being British and talking about the weather, I just now need to move on. But that's a general idea of conditional probability, and it has a formula. Yes, so the formula is the probability of A, given that B has already happened, is equal to the probability of A and B divided by the probability of just B. Now, where does it come from? Yeah, you'll find out in a moment, actually, and draw a tree diagram. But it's one of those that you just need to remember. And that line, that vertical line there, is the given that sign. So wherever you see the words in a question, given that, is very much asking you to use this conditional probability. And as I said again, it is the probability that both of the events happen, all right, the union of both, the intersection of both, divided by the probability that just B happens. Okay, so you've got that? Brilliant. Now, when I rearrange this, getting rid of that line because it's confusing me, actually what I end up with is the multiplication rule of probability. And it simply states that the probability of A and B is equal to the probability of A given that B multiplied by the probability of B. All I've done is rearrange these formulas. Now, what is really, really important to note is this B, after the given that, must be the B on the bottom of the formula. I could alternately write probability of B given that A is still the probability of B and A divided by the probability of A. That A is after the given that sign, so the A has to be on the bottom. Now also remember that the probability of A and B is going to be exactly the same as the probability of B and A, or B intersection A. Why? Because if you draw a Venn diagram, and we put those two circles, then that overlap is going to be the same whether it's A and B or B and A. Anyway, I'm waffling on. So using this multiplication rule of probability, let's look at some tree diagrams. And again, tree diagrams deal with outcomes of experiments. So hoping my head doesn't get in the way, this is going to be my start, and I'm going to have two events, M and F. Now you may turn around and say male and female. No, monkeys and flamingos. And you're going to say monkeys and flamingos. Well, believe it or not, back in the United Kingdom, my dad goes to a club where one day, no word of a lie, I walked through and on the notice board there was an event happening called snail racing. Can you think of anything more boring? Snail racing. I'd rather watch paint dry, and by that I mean really slow drying paint. But yeah, watching a snail go across this screen all that time would be really, really dull. Right, still with me? Yeah, good, good, good. So let's have monkeys and flamingos racing. That would be an interesting match. And obviously there's going to be an opportunity of the monkey winning or not winning, and my flamingo winning or not winning. So this is where the interesting thing is. I can actually replace this here and actually say that this section here, that probability there is winning given that monkey. This one here, not winning given that monkey. And this one here, winning given that flamingo, and not winning given not flamingo. Now again, don't be confused. It's only applying to that particular line there. Okay, that is the probability of winning given that it's a flamingo. And this one here, probability of not winning given it's flamingo. Now I'm going to just write some random probabilities on here. 0.3. What am I doing? 0.8, 0.21, 0.79, 0.4, and 0.6. So you can see there the probabilities are different. How, if you remember, do we get to the end of each line? What do we do if I wanted to find out the total probability? What would I actually do? Well, I would multiply those two together. So to get to the end of this line, I would have the probability of a monkey and winning would be equal to the probability of winning given that it's a monkey multiplied the probability that it's a monkey. And lo and behold, what do we happen to notice here? Yes, they're exactly the same thing. So that is the multiplication law of probability, just expressed in a bit of a tree diagram. Yeah, and we could actually continue to do all of this. This would be the probability of not winning and monkey. And again, it doesn't matter which way around those two go. I'm just trying to trick you. Would be the probability of not winning given that it's a monkey times by the probability of monkey, and so it goes on. So what can we do to use this information for bigger picture things? I mean, could we use it to work out the probability of winning, for example? Well, yes, if I wanted to find out the probability that something had won, then I would be looking for this event here and this event here, wouldn't I? Yes? So let's just write this out longhand. The probability that it is won and female is the probability of winning given that it's female times the probability of it being female. So if I want to find the probability of me winning, and I'm going to run out of space here, I'm just going to add those two together. So it's the probability of winning given that it's male times the probability of male plus the probability of winning given it's female times the probability of female. And ladies and gentlemen, although I can write it with A's and B's and all sorts of different letters, essentially this is the total law of probability, or law of total probability. Yeah, it's nothing more than just coming from my tree diagram. Do we use it? Me personally, I don't think I've ever seen a question where we actually would have to write out that formula and use it, but you never know. One day there may be a question. Alternatively, I have to say the best thing I ever do with probability questions is always draw a tree diagram where I can, even with conditional probability. Now, going back to tree diagrams and tables, we've done the tree diagrams and here is a table. Now, this question's come from the Cambridge Essentials textbook series. Cambridge have been very, very kind to allow me to use this because I'm actually using it as part of my teaching program. So videos are going to go to the kids that actually watch. And if you're watching it on YouTube, that's awesome as well. So as part of an evaluation of the school canteen, all students in a senior secondary college, years 10 to 12, were asked to rate the canteen as poor, good, or excellent. The results are shown in this table here. What is the probability that a student chosen at random, and I think it's really important to note that it has to be at random, is in year 12. So if we want the probability they're in year 12, how many are in year 12? There are 80 total. So my answer to part A would be 80 divided by 400, which would be 8 over 40, or 1 over 5. Easy peasy lemon squeezy. So far so good. Nothing to do with conditional probability. What about B? Is in year 12 and rates the canteen as excellent. Is in year 12 and rates the canteen as excellent, which is 35. So, part B, the answer is 35 over 400. which, when we cancel it down, is 7 on 80. Again, nothing to do with conditional probability, but reading this information from my table. What about C? Is in year 12 given that. So I want the probability is in year 12 given that they rate it at excellent. So I'm going to write that. So it's the probability they're in year 12 and excellent divided by the probability that it's excellent. Now, because I'm dealing with the same number of kids, the great news here is I just need to divide it by the top numbers, the actual totals. So the probability they're in year 12 and excellent is 35. Divided by the probability who found it excellent. Well, the people who found it excellent in total were actually 160. So when I cancel down 35 over 160, I get 7 on 32. And part D rates the canteen as excellent given that they're in year 12. Now that's interesting. Would you expect those to be the same thing? Well, no, because this is an example now where I'm going to be dividing by the number who are in year 12. So again, the probability that they are excellent and in year 12 divided by the probability they're in year 12. I'm running out of room. So let's move it up for a moment just to make sure my table, excellent and in year 12, same number, 35, divided by the probability that they're in year 12. So how many people are in year 12? There are in fact 80, which when I cancel it down gives me 7 over 16. Okay, if you've noticed that I keep fading in and out, so I can use my calculator to cancel this down. I can't be doing this in my head. All right, so the given that is really, really important. But ultimately, it's about whether you can then apply that to a formula. My advice to you is every single time, write your formula as probability of A given that B is the probability of A and B divided by the probability of B. I keep telling my students to do this over and over again. Hopefully, one day, they may listen to me. Now, independent events. We already talked about that a moment ago with regards to tossing a coin. Now, the great thing is that when an independent event it doesn't actually matter what has gone before, because the probability of getting something the second time is exactly the same as the probability it was the first time. It doesn't matter what goes before. So the great thing is we can see that the conditional probability of A given that B for independent events only is actually just the probability of A. Doesn't matter what has happened before, okay? And again, just as I say, if you think of the sentence as the probability of A given that B has already happened. So what is the probability of A happening given that something's already happened? Well, I don't care. They're independent. A is A. If I toss my coin the second time, it's still a half. And this is one of the great tests for whether things are independent. So when you work out questions, and they'll give you all sorts of questions. And by the way, you can't just look at this and know it's independent or not, all right? And if a question says, is the following thing independent? Don't just write yes or no, all right? It's really not a yes-no question. I mean, it is, but it requires you to do some actual working out. So knowing that, I can go back to my idea here that we had the probability of A and B was the probability of A, given that B's already happened, times by the probability of B. Yeah, I've just rearranged that formula around. Well, if they are independent, then we know that this value here is the same as probability of just A. So the multiplication rule of probability states that for independent events, the probability of A and B happening are the same as the probability of A multiplied by the probability of B. This is really, really important. Now, to go back to what I just said a moment ago, if a question says, are two events independent, not only do they want a yes or no answer, they actually want you to do some form of calculation. So here is an example that sort of puts that into count. The probability that Monica remembers to do her homework, so the probability that Monica remembers is equal to 0.7. So the probability that Monica forgets must be 0.3. While the probability that Patrick remembers, so probability of Patrick remembering is 0.4, and the probability that Patrick forgets is 0.6. If these events are independent, all right, and they've given that information in them, what is the probability both will do their homework? Will do their homework, so they both remember. So the probability that Monica remembers and Patrick remembers, well, they're independent. And so the great thing is we can just multiply those two things together. It's equal to the probability that Monica remembers multiplied by the probability that Patrick remembers, which is 0.7 times 0.4, which is 0.28. That simple. And that Monica will do her homework but Patrick forgets. So the probability that Monica remembers but Patrick forgets, again, they're independent. So it's the probability that Monica remembers times by the probability that Patrick forgets, which is Monica remembers 0.7, Patrick forgets 0.6, which gives me 0.42. There you go, ladies and gentlemen. That's it. That is conditional probability and independence. There are a lot of questions that are about to come forward in this particular topic, but don't worry about it. It's fine. You've got this. Oh well, thanks very much for watching. I'll look forward to seeing you next time. Now, if you haven't already, why not do me a favor and hit that little subscribe button, all right? Or go out there and tell your friends to hit subscribe. And if not, there's another video loading there for you to watch if you wish to. It's been good seeing you. I look forward to seeing you next time.